Hi all, I'm Sruthy and I'm going to talk about a novel method we have proposed for power and display rate adaptation in wideband NOMA in frequency-selective channels. This is a joint work with Professor Nilesh P. Mehta and we both belong to Next Generation Wireless Systems Lab at IISc Bangalore. Let's get started. So, NOMA stands for Non-orthogonal Multiple Access. In NOMA, base station serves multiple users in the same time and frequency resources. In power domain NOMA, as the name suggests, the base station transmits with different powers to these users. Let's take an example in which there is a downlink transmission which has two users. There is a near user, there is a far user. Near user uses successive interference cancellation to remove the far user's signal, and after that it decodes its own signal without any interference. Whereas the far user decodes its own data in presence of interference from the near user. In this way, NOMA helps to improve spectral efficiency, massive connectivity, and user fairness. It also lowers the transmission delay and achieves a higher cellular user throughput than orthogonal multiple access, which has been currently used. To employ power domain NOMA in 5G NR, there are some constraints which we have to satisfy. As we all know that OFDM is the physical layer in 4G and 5G standards. Depending on the data rate of the users, the scheduler at the base station assigns multiple physical resource blocks, PRBs, to these users. Due to the nature of frequency selectivity of the channel gain varies across these PRBs as shown in this figure. But at the same time, the standard mandates that the same modulation and coding scheme, MCS, and power must be used on all the PRBs assigned to a particular user. It limits uplink feedback and downlink control signaling overhead. This MCS belongs to a pre-specified set which is given by the standard and it is discrete. Next, look into the power domain NOMA in a frequency-selective channel. Let's consider the same example, and L1 is the path loss for the near user and L2 is the path loss for the far user. Here, the same NPRBs are being shared between the two users. Here, we have to find a common MCS M1 and power P1 to assign to all the NPRBs for the near user. Similarly, we have to find a common MCS M2 and power P2 to be assigned across all the NPRBs for the far user. For that, we need to track the SINR of each PRB of each superimposed user. Let's first look into the near user. As I already said, it decodes far user's data first. For that, the SINR is given by signal power from the near user, from the far user, and the interference is from the near user plus noise power. And after that, it cancels out the far user's signal from the receipt signal and decodes its own data. So here only SNR comes, no interference is there. Whereas at the far user, it decodes its own data in the presence of interference from the near user. So our goal is to choose the MCSs M1, M2 and powers P1, P2 subject to block error rate constraints of the two users. To achieve that, we formulate our problem statement such as maximization of weighted sum rate. Here, W2 is the weight given for the far user. We always choose W2 greater than 1 to ensure the fairness for the user fairness for the far user. And this is the block error rate constraint of user 1, this is the block error rate constraint of user 2, and a total power constraint and an SIC stable constraint. In SIC stable constraint, we say that we always allocate more power for the far user than the near user. So we have to solve this problem. What is the issue with this? The main difficulty here is that we don't have any closed form expression for the block error rate of an MCS when it gets transmitted to a vector of SNRs or SINRs. Here, this gamma 11 is a vector of SNRs or SINRs. So, to tackle this problem, we propose to use exponential effective SNR mapping EESM. So in EESM, it maps frequency-selective channel into frequency-flat channel. As shown in this figure, there is a vector of SNRs gamma 1, gamma 2 up till gamma n, and we map this vector of SNRs into an equivalent scalar quantity called gamma effective using this expression. Here, in the right-hand side figure, we show the effectiveness or the accuracy of the EESM. We plot the block error rate as a function of SNRs for 3 different MCSs. Here, the blue solid curve is shown for the AWGN channel and the scatter plot is shown for EESM. For all SNR values and for all the MCSs, the scatter plot almost overlaps with the solid curve. And EESM has been extensively used in 3GPP system level simulations. Thus, after using EESM, the problem statement becomes like this. Maximization of weighted sum rate subject to block error rate constraint of the 2 users. Here, saying block error rate of user 1 less than or equal to epsilon is equivalent to say that the effective SANR of user 1 by using the EESM equation greater than or equal to some threshold value Tm1 which correspond to that MCS. And the block error rate constraint of user 2, there is a total power constraint and an SIC stable constraint. The effective SANR of user 2 is given by the EESM equation like this. And from here, we can see that the effective SANR is nonlinear in powers P1 and P2. So we had to solve this problem. For that, as I have already mentioned, the MCS set is given by the standard and it's definite. So let's say there are total m possible MCSs available and we have n square possibilities for the MCS pairs and m1 and m2 can take from 0 to m. So here, for each MCS pair, we have to check whether a feasible power allocation P1 and P2 exist or not. If they exist, we say it as feasible MCS pair. Otherwise, it's infeasible. Here, all the green ones are the feasible MCS pairs. And the red ones are those infeasible. And among the feasible MCS pair, we choose the one with highest weighted sum rate. That is the optimum MCS pair. We solved it. But how to find or how to determine the feasibility of an MCS pair? For that, we are proposing a barrier function based method. And here we define barrier function f to be sum of 3 exponential terms. And each exponential term corresponds to the constraint in the problem statement. This is the block error rate constraint of user 1. This is the block error rate constraint of user 2. This is the SIC stable constraint. And whenever the inequality is not satisfying, the exponential function blows up. So we try to minimize f using gradient descent. A feasible solution exists if P1 satisfies all the constraints we have listed in the problem statement. And we say that an MCS pair is infeasible if no such P1 exists. So we have solved the problem statement, whatever we had discussed about. What is the issue with this? Here, we have to do a numerical search or a gradient descent for each MCS pair and each channel realization. The next question is that, how can we get rid of this numerical search? To answer this question, we propose power-normalized EESM. Let's recall that effective SANRs are nonlinear in powers P1 and P2. So to address this nonlinearity, we propose PNESM. PNESM of the kth user with MCS M is given by this equation, and this is similar to that of the EESM definition. But the only difference is that here the power term is replaced with alpha, which is a pre-specified constraint. So no more power term is showing up in the EESM definition. So the next job is to connect this EESM with the effective SANRs. For that, we are proposing two lemmas. In lemma 1, we connect the effective SANR of user 1 with the EESM of user 1. Here, the effective SANR of user 1 is upper bounded by the power scale version of EESM of user 1. And we have showed that this bound is exact for narrowband channels where the number of PRBs equal to 1. In lemma 2, we upper bound the effective SANR of user 2 using the SANR by the power scale version of EESM of user 2. Again, we have showed that it's exact for narrowband channels. So now we got the upper bounds for the effective SANRs of users 1 and 2. Now we use these upper bounds in the problem statement to make all the constraints to be linear in powers P1 and P2. So after using P and EESM, the constraints, the block error rate constraints will become like this. This is the block error rate constraint of user 1, and it gets mapped to something like this by using P and EESM. And block error rate constraint of user 2 is this, and it gets mapped to this. So the right-hand side of these two equations are linear in powers P1 and P2. Now we use these linear constraints in the problem statement and we solve the problem numerically. So we can easily draw the feasible region like this by using P and EESM to the block error rate constraints. So any P1, P2 from this region can be used further for processing. Instead of going for a numerical search or a gradient descent to check the feasibility of an MCS pair, we can just plug in these two conditions and say that whether it is feasible or not. So this is called P and EESM based method. Here, since this is a relaxation method, because we have used the upper bounds for the effective SANRs, it can lead to an infeasible MCS pair, and thus it overestimates the actual range. In such conditions, we have to use backtracking to find the feasible solution. Let's take an example. There are 4 MCSs available, and M1 and M2 can take 4 of these values. Here, the green ones are the feasible MCS pairs we got using P and EESM method. Let's say this is the optimal MCS using this method, and we check its feasibility using barrier function based method. If it is feasible, then we are done. Otherwise, we go for the next highest weighted sum rate MCS pair and check its feasibility using barrier function based method. If it is feasible, then we are done. Otherwise, we repeat these steps till we end up in a feasible solution. And this is called P and EESM with backtracking, PB. So next we move on to the numerical results in which we first check the effectiveness of PB with effective SANR based methods. Here we plot average weighted sum rate as a function of full power average SNR of the near user. L1 by L2 is the path loss ratios of the two users, and for all the path loss ratios and all SNR values, we can see that PB is as good as the effective SNR based method, and it has a lower complexity. Next, we benchmark our proposed method for wideband NOMA with wideband OMA. First, so here we are plotting average weighted sum rate as a function of number of PRBs n. As n increases, the average weighted sum rate of both wideband NOMA and wideband OMA decreases. Here, we can see that wideband NOMA outperforms wideband OMA for all L1 by L2 path loss ratios. Here, We also benchmark our model with flat fading or per PRB adaptation models, which has been extensively used in NOMA literature. So, from this figure, we can see that it overestimates these flat fading or per PRB adaptation models overestimates the actual weighted sum range. So we can conclude our discussion now. We have seen that NOMA in 5G and OFDM must adhere to new constraints and operate over frequency-selective channels. We have proposed a method based on EESM for power and discrete adaptation in wideband NOMA. For that, we have proposed a EESM-based method and developed its theoretical basis. We have showed that PB works as well as the effective SANR-based method, and it has a lower complexity. We also showed that the per PRB adaptation assumption, which has been extensively used in the NOMA literature, overestimates the average weighted sum range. That's all. Thank you.